Okay, welcome here last week. Final coming up next week. We're in chapter 11 as we went back to it. Which got a little bit more to sort of finish up, and then we'll get into maybe a little bit of last piece of information. So really in chapter 11 last time, what we were talking about was electron configuration. And remember, electrons go into the atom lowest energy level first. They fill it, and then they go to the next lowest, and they continue this sort of path of putting electrons in the lowest energy levels until they're full. Remember that each individual sort of orbital, which is what that sort of represents, could hold a maximum of 2 electrons. And that's what we sort of ended up talking about last time at the end. We think about electrons being in these sort of probability maps, as there's no good way to know exactly how electrons moving or its position at any given time. That's sort of the Heisenberg uncertainty principle. So the best that we could do is sort of come up with these sort of probabilities of there's probably a high probability of finding a location, an electron in a particular location in an atom, versus maybe there's a lower probability of finding an electron. And the idea with the probability is, even if there's sort of a low probability of finding an electron in a particular area of the atom, doesn't mean that you won't find one. That just means there's a lower probability of finding one, say, closer to the nucleus. So where we have electrons in the atom are in these orbitals. They're sometimes referred to as atomic orbitals. And there are s orbitals, which there's only one type of s orbital. And it does begin, as we talked about, on the n equals 1, which is the principal quantum number or the energy level. And that n equals 1 is the lowest energy level there is. That means if there's only one type of orbital there, and any s orbital will hold a maximum of 2 electrons in that particular case. Now, there's also p orbitals, and p orbitals, there's actually 3 different types of p orbitals. There's that px, py, pz, sort of the orientation in 3-dimensional space. They do not begin until you get to the second energy level. So on the second energy level, that is where we start to see the p orbitals begin. And because there's 3 different types of p orbitals, each one can hold 2. That is a maximum of 6 electrons if you feel what we sometimes refer to as the p subshell or sublevel. So when you have a subshell or sublevel, it is a grouping of individual orbitals together on the same energy level and the same type. Like we have that with p orbitals, d orbitals, and f orbitals. We get those sort of subshells that occur. Speaking of d orbitals, d are the next type of orbitals, and there's 5 different types of those. They do begin on the third energy level. And because there's 5 different types, and you can put 2 in each, that is again a maximum of 10 electrons if you fill up the d subshell. Once again, you don't need to fill up necessarily a whole subshell. You just need to use however many orbitals that you need. But that is the maximum you can put in there if you did fill it completely up. Lastly, there's f orbitals, and there's actually 7 different types of f orbitals. They do not begin until you get to the 4th energy level. And that means that there's 14 electrons in that subshell if you basically fill it all up. Now, there is a specific order at which those electrons go in, as I mentioned before, lowest energy to highest. And there is some difference in how you might think the orbitals are in terms of energy. So you can make that chart that we talked about by actually just knowing this as well. Again, this is how you could just sort of recreate that chart. On the first energy level, there's just an s orbital. Down to the right, second energy level, p orbital. Down to the right there, d start, and down to the right, f start. As you sort of line that up, kind of your 1, 2, 3, 4, all you have to do is essentially just put the numbers underneath each of them. You go up to 7. And obviously, if you didn't run out of room like I did, you could go up to 7 there. You could also obviously continue to do this guy as well. And obviously, again, we always start up on top, and then we continue to sort of zigzag. Again, the area where people usually will kind of screw this up is coming through here. Again, the 4S does come before the 3D, and that pattern follows basically all the way through. Again, you can see the 5S there before you get to the 4D. So they do continue to sort of follow that pattern as you go through there. So you always want to start at the top there, follow the arrow, and then come back to the back of the arrow, follow the next arrow, kind of zigzag back and forth. If you know pretty much both of these things here, how many you can put in and that, you should be able to write any type of electron configuration that you would need to write. So for example, if we looked at sodium, which is 11, it would be 1s2, 2s2, 2p6, 3s1 in this case. Remember, that's the proper way to sort of write it and say it. The first number again is the energy level, or really the principal quantum number. And that's that N number. The letter is the orbital or subshell, and electrons are in. And the top number is the number of electrons in an orbital or subshell. Once again, there's no weird things like commas, dashes, anything like that. So that again is how it should look. We also talked about drawing orbital diagram where you could use boxes or lines to represent the different orbitals. If you're drawing this correctly based on energy, you should be going upwards. Again, I'm just going sideways to prevent running out of room here. There's some really badly drawn boxes there, I suppose. Let's fix that up a little bit there. And when electrons go in, as we talked about, they do always go in sort of the first one in the uppers position. That's what's known as having positive spin. And remember that when we share two electrons in any individual orbital, they always need to have opposite spins so they don't violate Pauli's exclusion rule, and that will prevent them from having the same four quantum numbers. This arrangement here is what is referred to as being paired spin, as they're going in opposite directions. That is again how they sort of feel when we get to a subshell sort of situation where you have multiple orbitals. Hund's rule tells us the stablest situation is to maximize the parallel spin. So they do go in one at a time in the upwards position, and then they do come back, and when they have no choice, sort of pair off. So that's always sort of how they would go in there. Now, lastly, we talked about there's also sort of a shorthand. If you take just this part of the electron configuration, that is 10 electrons. And if we look on the periodic table, 10 is neon. So we could put neon in brackets and continue on with the configuration. This should always be a noble gas that comes right before the electron configuration that you're writing for that particular element. And again, it represents basically neon's electron configuration, then you continue on. Any questions on any of that stuff there that we talked about last time? Okay, so then let's talk a little bit about electron configuration and ions. So obviously there are cations, as we talked about a number of times, which are positively charged, which means they have lost electrons basically, or lose electrons. There's also anions, which are negatively charged, and again, that is a result of them gaining electrons. So when we do have things with charges, we do need to adjust our electron configuration. So if we look at, say, our friend there, sodium, and again, sodium with no charge, 1s2, 2s2, 2p6, 3s1. A reminder that we can look at the electron configuration and figure out how many electrons are on each energy level. So on the first energy level, we have 2. On the second energy level, we have 8 electrons. And here on the third energy level, we actually have 1 electron, which is the highest energy electron. That is what is sometimes, as we'll talk about, known as valence electrons, as we talked about when we did bonding and all that good stuff. These lower energy electrons are sometimes referred to as core electrons. So when we do sort of lose electrons or even really gain electrons, they usually do end up sort of in that valence electron sort of orbitals. So if we have something like sodium, which has a +1 charge, means it lost one electron, it has only 10 electrons, it is going to really lose this outermost electron. At its highest in energy, it's not going to be held as tightly. It's going to be a lot easier to remove. And we would have an electron configuration of 1s2, 2s2, 2p6, or that is the same electron configuration as neon in this particular case. Now, if we look at something like nitrogen with no charge, it's got 7, which would be 1s2, 2s2, 2p5 in this case. No, it would not be 5. It would be so 7, that's 4, 3 sounds good in this case. There we go. And it has 5 valence electrons here. And has 2 sort of core electrons there on the bottom. So when nitrogen gets a charge, it will be a -3 charge, which means it has gained 3 electrons and becomes 10 electrons and has an electron configuration of 1s2, 2s2, 2p6, or again, that is still neon. Remember that pretty much this is what is known as being isoelectronic. Has the same electron configuration. Sodium with a +1 charge, neon and nitrogen with a -3 charge. They all have the same electron configuration. And this is normally what happens, as we talked about when we did bonding, the idea of ionic bonds. When somebody loses electrons, especially the representative metals in group 1, 2, or 3, they lose enough electrons to back up to the noble gas that comes right before them. And that's what we see with sodium. It loses 1 electron, moves it back on the periodic table to neon, which makes it really, really stable. Something like nitrogen will gain 3 electrons to move forward on the periodic table to neon, which is also a noble gas. Remember, that's really the purpose, as we talked about when we did bonding, of all bonding, ionic bonding, covalent bonding, is for everybody to achieve that noble gas configuration. Now, it's also important to remember, as we did talk about, that they do not become that element. That's because they still have this right number of protons to be sodium or nitrogen. Nothing changes in terms of protons. But in terms of their electron configuration, they end up in this really stable sort of noble gas configuration, which makes everything work and be very happy in that sort of arrangement. Any questions on that? So when we talk about representative elements, which is our guys really 1 through 8 on the periodic table that are normal numbering, they will either gain or lose electrons and really end up at a noble gas. Now, are a little bit different in terms of what happens with them when we look at transition metals. There's a couple that sort of happen. S orbital being lower in energy than the 3d orbital. What happens though, as we start to put electrons into the d orbitals, they actually do kind of switch places in terms of energy. And what happens is we actually end up with the 4s orbitals being higher in energy than the 3d orbitals, right? And this is really important in terms of what happens when they lose electrons. This is also why when we talked about transition metals at the very end as well, there are 2 sort of exceptions to sort of the normal electron configuration that you should be aware of. And again, that is chromium, which is 24, and copper, which is 29. And again, if you follow that zigzag chart with 1s2, 2s2, P6, 3s2, 3p6, 4s2, 3d4 for chromium. they are really close in energy. It doesn't take a lot of energy to sort of promote up one of those lower energy electrons, or the s electrons, or really in this case, drop it back down. And what happens is they actually have one more electron up in the s, I'm sorry, up in the d, and one less electron in the s orbital. Up through here is 18, which is argon, and it's 4s1, 3, 5. Copper has a similar sort of exception, which is argon 4s1 3d10, and again instead of 4s2 3d9. So these are the two I said you should remember and use in most chemistry classes that you take. Those are the two that you should look at and always know. A lot more exceptions just like them. Silver, for example, as we saw, is an exception. Something like PD has no electrons in the S's. They've all been sort of promoted up to the D's. So there's a lot of other sort of exceptions as you go through that transition metal region below chromium and copper there on the periodic table. But most chemistry you take that you definitely should know. Switching that occurs when transition metals actually do go to lose electrons. They're going to take energy electrons first. So because of this switch that occurs, the transition metals will actually lose the s electrons first. And then if they need to lose any more electrons, then they will start digging into the d orbitals there to pull out any more electrons that they may need to lose. So transition metals, when they do form ions, are a little bit different than what happens with our representative elements, especially our representative metals. Pretty much is the last guys that you write in electron configuration are going to be the ones you're going to remove. But here it's always going to be the S followed by the D if necessary. So if we look at something like iron, which is 26, we would have an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6 here. Once again, this is argon's configuration, so we could argon it and 4s2, 3d6. So if we look at sort of what's happening, the orbitals with those electrons, we do get this switch energy that occurs. We will have electrons looking like this in 3D. So one thing like iron, for example, will lose some electrons. Let's say it makes a +2 charge. That means it has lost 2 electrons, so it will end up with 24 electrons in this case. And when we look at it, these are going to be the very first electrons that will be lost in this case. So they're going to lose these because they are higher in energy. And that would leave us configuration, if I just shorthanded here, argon 3d6 in this case, as we lose those kind of 2, 4s electrons. Question on that there. Now, if we went to iron that had a +3 charge, it would then be down to 23 electrons. Same thing is going to happen. We're going to take off these 4s electrons first, but now we will have to dig into the D here to lose that third electron, which would be like that guy probably right there. And that would leave us argon 3d5 in this case. So transition metals are a little bit different. Like I said, always the S's, and that happens all the way through the transition metal region. They will always dump those S's off first, and then the P's will kind of follow. And if we look here, right, this is sort of our, as we talked about, blocks on the periodic table. The first 2 columns, which are the S block, 3 through 8 is the p block, which has 6 electrons. Our transition metals here have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's our D block here. And down here is really our F block, which F has, if you fill up the subshell, 14 of them. If you count all the way across there, you will have 14 little boxes. So as we talked about before, you can kind of use this to count off electron configuration. You have to be careful, but if we went to like sodium like we did before, that would be 1s2, 2s2, 2p6, and 3s1. Now, if we went to our iron, which is right about there, we could also count it off, and we look at it here. So if we started up on top again, this would be 1s2 to there, 2s2 equal to the period number is the n number, 2p6, 3s2, 3p, 4s2, 1, 2, 3, 4, 5, and 6. Problem is, though, you got to remember that D's do not start until the third. So that again is, as we talked about at the end last time, that is 3D, not 4D. So the D's are one behind the period number here. This would be 4D, 5D, and so forth coming down. Same thing with our F's, which are down here. That is basically 4F, and that is 5F, which are 2 behind the period number if you do that. So it does get a little kind of crazy there in the transition metal region. If you're not really sure what you're doing, you might kind of mislabel something. So again, that zigzag thing is pretty good. But speaking of our transition metals here, they all, since as we can see here, they will always dump these guys out before they go kind of dish out the D's if necessary. Again, you got that sort of pattern happening all the way down there. So transition metals will always lose those S's first. They will not get themselves back to a noble gas because frankly, they got a long way to go to do that. So they won't really back up to a noble gas. But what they're able to do is sort of stabilize themselves by releasing the really highest energy electrons, and it becomes a little bit more stable in that sort of situation. But they, unlike representative guys in group 1, 2, and 3, they won't back up to a noble gas when they lose electrons, as we saw here in this example. Obviously, we're still in the D's. We didn't get back to a noble gas or anything like that with our transition metals. That's also why when we think about transition metals, most of them will have sort of the ability to make multiple or variable type of charges. Because they got a number of sort of combinations or electrons that they can kind of lose in certain situations. And that gives them the ability to have more than one type of charge, as opposed to kind of representative guys, which pretty much have just the electrons at the end there. And those valence electrons don't have those extra Ds, and they're just going to make those sort of fixed charges. Any questions on that there? All right, so why don't you try a few? Why don't you do, let's do calcium with a +2 charge. Let us do Br minus. Let's do Mn4+, and a little nickel 2+. Write the electron configuration for each of these guys here. Calcium is 20 on the periodic table. Bromine is 35. Mn is 25, and nickel is 20. Yeah, let's take a look and see. So calcium has 20 normally, which means with a +2, it should end up with 18 electrons. So that's going to get us 1s2, 2s2, 2p6, 3s2, and 3p6. That is also the same, obviously, as argon's configuration. And again, that's representative metal, so we expect it to back up to the noble gas right before it. Any questions on that one there? Br minus means it's gained 1 electron, so instead of 35, it should end up at 36, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and after that, we should go back here to 4p6. That is 36, which all together ends us at krypton here in terms of our configuration. Any questions on that? And again, here a representative element gaining an electron going forward to the noble gas that comes after it on the periodic table. So it ends up at krypton's configuration. Now coming here to our Mn, that is going to be 25 less 4 electrons, means it's going to end up actually at 21 in this case. So if we look at again Mn here with no charge, that will be argon 4s2 3d5. So again, with no charge, that's what we're looking at. So here's going to lose 4 electrons. So we are going to take our first ones, which are going to be the S's. That's only 2 electrons, which means we do need to delve into there and take out 2 from there. That is going to leave us with argon 3d3 in this case for Mn 4 plus. Questions on that one there. And lastly, here we have nickel with a +2, which means we go from 28, we lose 2 to 26. Once again, if we do nickel with no charge, we're looking at argon 4s2 3d8. And with a +2 charge, it's going to be those S's coming out first. And that's going to give us then argon 3d8 in this case. Any questions on electron configuration with things with charges? Transition metals, regular metals. Okay. All right, so clearly you need to be able to write electron configuration, charges, no charges, transition metals, and all that good stuff, and be able to draw the orbital diagram. Let's talk a little about some other things, including some periodic trends to officially talk about it. Obviously, our valence electrons, as we talked about throughout the semester, are those highest energy electrons. They can be found by a couple of ways. You could write the electron configuration like we see here. This is for nitrogen. And here, these are the highest energy electrons on the second energy level, and there are 5 of them. By just counting up the electrons from the electron configuration. The valence electrons are important electrons because they're the first ones away from the nucleus. They're not held as tightly. They're also the ones that are involved in bonding. So all bonding pretty much goes through those valence electrons. Remember the core electrons, which are much closer to the nucleus, pretty much do not participate in bonding because of some of those trends we're going to talk about. Clearly, a much easier way to figure out our valence electrons is by going by the group number. So by going by the group number, it will equal the number of valence electrons, much like we did when we drew Lewis structures and other things. So there in group 5, we see our nitrogen, which has those 5 valence electrons. Chlorine or fluorine has 7, and if we did our fluorine's electron configuration here, all right, there's the 7 valence electrons in those second energy level orbitals is basically where they come from. So the number of valence electrons equals group number is really the easiest way to do it, although a lot of times you don't really need too much in terms of valence electron for transition metals. You could also do a similar thing. It will equal the group number for the transition metals, but it is the group number more like kind of the B numbering or just the straight 1 through 18 type numbering. So as we just talked about in our representative elements, everybody in group 1 will have 1, 2, 3, 4, 5, 6, 7, and 8, except for obviously helium that only has 2. because that's the only number of electrons it has. Now, when we talk about our transition metals, if we were just to kind of number our periodic table, just starting at 1 and going to 18, this would be group 1, right? This would be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then obviously this would be 13, 14, 15, 16, 17, and 18 coming across. So when we talk about sort of valence electrons in our transition metals, because they have the S's available to them and also the D's available to them, it also equals this group number. So that would be 3 for like this guy. He's got those 2 S's and 1 of those D's. Guy next to him has these 2 S's and 2 D's and so forth. If we get to our iron here, which was argon 4s2 3d6, it has those 2 S's and 1, 2, 3, 4, 5, 6 more, and those would be the valence electrons considered here for our iron. So when we get transition metals, if you want valence electrons, you want to go by just the regular 1 through 18 sort of numbering that covers there. But you do want to remember when you switch back here to our representative numbering, that also switches back to number of valence electrons. So again, 3 valence electrons, 4, 5, 6, 7, and 8 valence electrons out here. So in the middle, kind of the normal numbering up to 12, and that it will tell you the number of valence electrons, and then it kind of switches back to our 3, 4, 5, 6, 7, and 8. Any questions on that there? Now, with all these sort of periodic trends and like that experiment you did a while back, what we saw was that most of the active metals are found kind of to the left and down on the periodic table. That's really where you find your most reactive metal. If you ever saw a comparison of how, say, lithium, sodium, and potassium react with water, potassium reacts much stronger than lithium does, and it does even more than sodium does as well. And that's because reactivity increases as you go down a group there on the left. And as you saw when you did that experiment with the halogens way back when, week, whatever it was, 4 maybe, or 5 or 6, when you had the different layers and you saw the color jump from the top layer to the bottom layer and all that kind of stuff, you saw the reactivity of halogens increase as you went up group 7. Fluorine more reactive than chlorine, chlorine more reactive than bromine, bromine more reactive than iodide. And that's because as we go to the upper right of the periodic table, that is where we find our most reactive nonmetals, pretty much fluorine. And it's really because of these periodic trends we're going to talk about, or have talked about, and official will talk about here, as to why we see that. So one of the important trends is effective nuclear charge. And effective nuclear charge is the charge that essentially the electrons actually feel from the positively charged nucleus. And for example, if we look at something like lithium, 1s2, 2s1, it has 1 valence electron, got some core electrons happening there. And because it's really sort of charge, and on the first level, it's got a couple of electrons. Level also got an electron kind of flying around randomly. Now, these lower energy electrons, they pretty much will feel the full brunt of that +3 attraction to the nucleus. And as you may remember, when we talk about positive and negative attraction to one another, the strength of that attraction is based on the charge. So if you have like a +3 and a -3, that's going to be strongly attracted to each other, stronger than, say, a +1 and a -1. So as the charges increase, you get a much greater attraction between these things. Now, when we look at the valence electron, is our guy way out here, our valence electron. What he's actually experiencing is what is known as shielding. And he is being shielded by these lower energy electrons. So these lower energy electrons are actually shielding the positive charge from the nucleus. And that outer valence electron is not going to feel the exact same positive charge as those lower energy electrons do in that +3 sort of situation here. And you could actually figure out the effective nuclear charge, which is essentially what that electron is feeling. And you could take the positive charge from the protons and subtract it from the number of electrons that are shielding. So there's 2 below it. So instead of that outer electron here feeling a +3 sort of attraction to the nucleus, it's actually only feeling like a +1 attraction, which means it's not going to be pulled in as tightly to the nucleus because it's not feeling as strong of an attractive charge. That's also why that valence electron can be easily popped off, much easier than those core electrons, which are going to be pulled in much tighter by the greater positive charge in this case. Now, electrons in the same energy level don't really shield each other. It's just ones higher energy are shielded by the ones in lower energy level. And that accounts for what we see in terms of those outer electrons not being held as tightly. The general trend on Z effective is it increases as you go up and to the right on the periodic table and sort of decreases as you go down. As you go to the right on the periodic table, you have a lot more protons. A lot more protons are going to cause a greater positive charge, going to bring in those electrons a lot closer. Even those outer ones will be brought in a lot closer. Any questions on that there? Now, ionization energy, as you may remember, is the energy that's required to remove an electron from the gas phase of an atom. And when it is lost there, it's on the product side here of an equation. And the result of losing electrons is that we become positively charged. We think about ionization energy for our cations. Those are the guys that become positively charged as a result of losing electrons. Metals have very low ionization energy, which means it doesn't take a lot of convincing to try to remove electrons from a metal. Nonmetals, on the other hand, have very high ionization energy, which means it takes a lot of effort, if you will, to try to rip an electron out from a nonmetal. And it doesn't usually happen because of that. The general trend on the periodic table is it increases as you go up to the right and decreases as you go down. Also, a reminder that electrons actually do come off one at a time. So, for example, if you took magnesium, the first thing that would happen is it would lose 1 electron. Then this guy that has now lost 1 electron will then lose another electron. And so forth. And each time that an electron is lost, there's an ionization energy associated with it. So the first ionization energy is the energy required to remove the first electron. Second ionization energy is the energy required to remove the second, and third, and fourth, and so forth. As we may know as well, as we lose the first electron, the size of the atom will shrink as it becomes an ion, as it loses some of its electron cloud, and it will bring everybody in closer as a result of that. And that means that it actually does get harder and harder to remove electrons after you remove the first one. It goes from the second to the third, for example, it gets much higher in energy, to the point of it is not energy efficient to remove a certain number of electrons at some point. And in the case of magnesium, we know it is group 2, so it makes a +2 charge. And that's also because when we look at the electron configuration for our magnesium here, it has 2 valence electrons. So not too bad to remove the first one, gets a little harder to remove the second one. Next one, maybe you're doing like a 7-8 fold jump in energy if you wanted to try to do that. And it doesn't happen under normal cases because at that point, everything got really small and these core electrons are much closer to the nucleus, and it's just not energy efficient to get those guys to come off. So that's why we only lose those valence electrons in that particular case. Any questions on that there? And that's what we see on this table. Here's our magnesium, 735 to remove the first one. We kind of double it to remove the second one. So it gets harder to pull off that second electron. And now as we try to jump into the core electrons, we're about 6-7 times the amount of energy would be required, and it just doesn't sort of happen as you continue that way. Same thing here if we look at aluminum, which is +3. First one, not bad. Second one doubles. Third one doubles again. But look at the jump as you try to get into those core electrons. At that point, it's like 11,000. Just not going to happen. And that's, again, why aluminum, for example, will lay it up there after the third electron, and it loses its third valence electron. It's just not energy efficient for it to try to rip off those core electrons. It's not going to happen very efficiently or greatly. And you can see there with silicone, you're jumping into, for example, 16,000, 21,000, 27,000, a lot of energy as you get into those core electrons. And again, doesn't typically happen. Now, electron affinity, on the other hand, is sort of the opposite process. It is the energy change that occurs when an electron is gained by an atom. The general trend in electron affinity is it increases as you go up and to the right and decreases as you go down. It's not a perfect sort of trend. We do see the electron on the reactive side here, like it's being gained in this case. And this is what we associate with anions in this particular case, something that becomes negatively charged. Now, this shouldn't be confused with something else that we talked about a lot, which was electronegativity. And electronegativity is that ability of an atom to bring electrons or attract electrons towards itself. Also increases as you go up and to the right and decreases as you go down, with our friend fluorine being the most electronegative element you have. So as we go up and to the right on the periodic table, we have things that have very high electron affinity, which means they're pretty good at accepting electrons. We also have things that have high electronegativity, which means, again, they want to bring electrons towards themselves as well. And that fits with our size as well. And when we look at the periodic table, as we go to the right and up, things get smaller. As we go left and down, everybody gets larger. And you can think about it as you go to the right again, you get a buildup of that positive charge. So starting out, you have a greater positive charge in the nucleus. And because of that greater positive charge, it's going to bring even the outermost electrons in a lot closer because it's a greater positive charge than you would have on the left-hand side in that situation. And that's what we see here as well. As we pop to the right there, things get smaller. And as we go to the left, it gets larger. So again, putting together all of our sort of periodic trends, like our Z effective increasing this way and decreasing this way, our ionization energy increasing this way and decreasing this way, our electron affinity increasing that way and decreasing this way, and our electronegativity increasing this way and decreasing this way. What we see is sort of what we've talked about all semester, which is up here where we have our nonmetals, we have things that are typically relatively small, which means they want to hang on to their electrons a lot. They also want to bring electrons towards themselves. And these are all things that do not want to release their electrons. They have very high ionization energy. And that's why we think of nonmetals as always sort of gaining the electrons and becoming negatively charged, as opposed as we go bottom left there, where we have metals. They have all the opposite sort of periodic trends. They have situations where they're really large, which means outer electrons are not held as tightly, lower ionization energy. You could just take them off with ease. They have really no issue of I want electrons. They don't want to hang on to their electrons. They don't want electrons to come towards themselves. And that's why we see metals typically become, again, positively charged because of all these sort of periodic trends. Any questions on that there? All right, so if we look at this, sodium and chlorine, which one's going to be larger? If we look, they are in the same row on the periodic table, which means our friend sodium there should be the larger atom as it's further to the left in that case. Which one should be the larger atom between lithium and cesium? These guys are actually in the same group, and we have cesium that is further down in the group, and that means that it should be the larger atom in this case. Which one is larger, the hydrogen 1s orbital or the lithium 1s orbital? Which one do you think is larger? Are they like the same? So the idea here is between the two elements, if we look at hydrogen, has basically a +1 charge, it has 1 electron. Here we have lithium, which is a +3 charge. So when we think about our 1s orbital here, because of this +3 charge here on the lithium, is a much stronger attraction to that 1s orbital, which means it's actually going to pull the 1s orbital in a lot closer. And because it pulls that 1s orbital in a lot closer, that means the overall size here of our 1s orbital is actually going to be a little bit smaller than this one, where there's not as strong of attraction. So it's going to be a little bit bigger because it won't pull that 1s orbital in so closely. So in this case, it actually should be the hydrogen one will actually be larger because of the less of a pull because of the nucleus. Any questions on that? With that being said, which one should be lower in energy? Because it's going to bring this 1s orbital closer to the nucleus. By definition, right, lower in energy is the ones closest to the nucleus. So it will pull that lithium in closer, and it actually will be lower in energy than the hydrogen 1s orbital, which again is not going to be dragged as far closer to the nucleus because it doesn't have as big of a positive charge. Questions on any of those there? And obviously here we're going to range according to ionization energy and atomic size. And if we look on the periodic table, it looks like this arrangement as to where their position is. Ionization energy increases this way and decreases this way, which means the lowest ionization energy should be sulfur, going up to oxygen and over to fluorine should be our order there. And in terms of atomic size, size gets smaller as you go that way and larger as you go this way, which means our fluorine should be our smallest, followed by our oxygen, and then to our sulfur in this case. Any questions on that there? Questions on periodic trends, how they relate to metals and nonmetals, gaining and losing electrons. That is chapter 11. Can't believe it. All right. About equilibrium, we'll officially talk about Le Chatelier's principle and all that stuff here. But a reminder that equilibrium doesn't necessarily mean equal, even though it kind of says equal in the name. And that's sometimes what people think about when they think about a reaction that's at equilibrium. Equilibrium reactions are actually specific types of reactions, which are the reactions that actually go in both directions. So these are what are referred to as being reversible reactions. And they have these arrows that head in both directions. And as we go from our reactants to our products, that is what is referred to as the forward direction. And if you start this reaction, for example, with just A and B, that is what you would expect to happen. Because there's only A and B present, you would expect this reaction basically to start heading towards the product side and making products. What will happen in this case is at some point, they will make enough products over here that these guys will decide we would like to go back the other way, basically. So they'll build up enough of those products that the products will start combining with each other and actually heading in the opposite direction, going from products to reactants. And that is what is known as the reverse direction. And this process will continue until it actually does reach chemical equilibrium. And what it means when we reach chemical equilibrium is the rate of the forward direction will equal the rate of the reverse direction. So really what we're talking about when something reaches equilibrium is not necessarily that you have the same amount of everybody on each side, but that the rate of the forward direction will equal the rate of the reverse direction. So just as quickly as you make products, those products will recombine and go the other way. What that essentially does is when a system reaches chemical equilibrium, it will essentially lock everybody into place in terms of their concentrations or their pressures. So, what will happen is if whatever concentrations they are at, the reactants, the products, when they reach equilibrium, they'll pretty much just maintain. They'll be able to maintain their concentrations. If we're talking about pressures and gases, they'll maintain their pressures because just as soon as you lose a little, it's just going to come right back and nothing's going to basically change. They're just going to get locked into place. And they will continue that pattern, pretty indefinitely unless you kind of do something to screw it up. And you can do things to screw it up, which is really the whole basis of the Chaudière principle. You kind of screw up the equilibrium. But they'll kind of go back and forth. So again, for example, here, if we had a reaction where we started initially with like 4 of this guy and 5 of this guy and none of these guys. And we eventually reach equilibrium. Maybe we got 2 of this guy, 1 of this guy, 3 and 4 of these guys. What will happen once they basically hit equilibrium is they're just going to maintain where they're at and none of those numbers are going to change. It'll be able to just keep them right there at those levels. Any questions on that there? So let's talk a little bit about how reactions sort of happen, and we talked about in some other chapters, especially with energy. And if you remember, there's sort of this idea of the collision model, which basically means in order for a reaction to occur, they got to kind of collide with each other. So molecules has to collide with each other. They do have to collide with each other in the right orientation. They has to hit each other sort of in the right active spot, if you will. Not all collisions that happen will actually lead to products being formed. It will result in maybe no products being formed if they don't hit each other in the right location or with the right amount of energy. So it's really important for that to happen. And as those guys collide, as we see here, what will happen is we basically will start breaking some bonds and then we will start making some bonds. So if you remember, we had sort of an energy diagram here, right? And if these are reactants, these are products, as it's coming up this hill, which by the way is the activation energy hill, right? And that activation energy hill is the amount of energy that's needed for this reaction to take place. They will get towards to the top of the hill, which is our transition state, if you remember. And that is where we got this transition state complex of partially made bonds, partially broken bonds, and then very quickly it will come over the hill, kind of to make our products really quickly, where we make our new results here that are formed. Remember, in a chemical reaction, we just break bonds, make bonds, don't do anything with the nucleus. So that is sort of the process that happens. Now, speaking of rates, there's a number of things that can affect the rate of a reaction. For example, the concentration can affect the rate of reaction. If we increase the concentration, we typically will increase the rate of a reaction. And if we think about something like molarity, which is a concentration, that is moles of solute per liters of solution. Remember that when we have a solution, it is actually the solute guys that are floating around. That is the stuff that is reacting, which means if we have a high concentration, we will have a lot of solute in that solution, which means we have a lot of guys swimming around. And it's not going to take very long for those guys to come in contact with each other and start a reaction to happen. And the same is true if we had a lower concentration. We had a lower concentration, you typically would see a lower amount of solute, which means maybe they're pretty sparse. And it's going to take longer for everybody to find each other. It's going to take longer for a reaction to occur because they're not going to be bumping into each other right away. They got to kind of float around, for example, for a while until they find somebody to react with. Or if it's a gas, they got to fly around for a little bit until they sort of find somebody to react with. Now, temperature plays a really big role in terms of the rate of a reaction. And if you increase the temperature, you typically will see an increase in the rate of the reaction. And for example, if you like increase the temperature like 10 degrees Celsius, you oftentimes could double the rate of the reaction and make it occur twice as fast in a lot of reactions. And the idea there is as you increase the temperature, maybe you take your test tubes and put it in a hot water bath before the reaction together or mix them together. That's going to add a lot of energy to everybody, which means a lot of energy. People are moving around a lot faster, going to cause a lot more collisions. And in addition, they're probably going to have the right amount of energy at this point because you kind of increase the temperature and the energy of the system, and that's going to allow the reaction to take place. If you lower the temperature, you take your test tubes, put it on ice, you're going to get these guys are going to be moving in really slow around. It's going to take longer for collisions to occur. They probably won't have as much energy or enough energy to get up and over that hill, and you'll probably see a lower rate of your reaction. So those are two really big factors in terms of how fast a reaction takes place. Here is our energy diagram. Again, reactants to our products. As it's coming up the hill, we're breaking bonds, starting to make bonds. We get this, which is it's very high in energy. That is, again, at pretty much the highest point in energy of this reaction. And as we know in chemistry, things in high energy are not really favored. Things like to be in low energy. So that being in the highest point in energy doesn't hang around a really long time. And as I said, it really will sort of complete its journey a lot of times really, really quickly by falling down the hill there to the other side. Another very common way that we could speed up a reaction is to add a catalyst. And a lot of times catalysts are written up on top of the arrow. And for example, a catalyst, though, is not a reactant. It is not a product. It is there really just in most cases to facilitate that reaction happening a lot more effectively and efficiently, if you will. It sometimes finds an alternative pathway for that reaction to take place. So, for example, if we had just gas molecules, just flying around by themselves, they kind of have to, fly around and try to find each other to react. Now, if you take something like a metal catalyst and slap it in there, what could happen is perhaps these gas molecules are attracted towards the metal catalyst. And what that's going to do is put everybody in a really centralized location. And now it's going to be a lot more efficient for that reaction to take place. They most likely will not have an issue of finding each other and sort of kicking off this reaction, and it will usually speed up. The result of sort of finding that more efficient alternative pathway is what it essentially will do is lower the activation energy. So what it essentially will do by finding that alternative pathway is those reactions just got to climb this hill basically to get to the other side, which is much smaller than if they had to climb the original hill, which is way over here. The result of that is you'll have probably a greater proportion of molecules that will have sufficient amount of energy to actually get up and over that hill to the other side. And that will result in your reaction happening faster. Again, the catalyst is typically not consumed in a reaction. It is not, again, considered a reactant or product. It's really there just for that sort of function. The catalyst will sort of be unchanged usually. Catalysts can be in the same state as what's reacting. So you can have, for example, if you're mixing solutions together, you can have a catalyst that's like an acid catalyst or a base catalyst that's also a solution. So they're in the same sort of phase as what's reacting. You could also have things in different phases like this. Maybe what's reacting are gas molecules and your catalyst is a metal. So you could have those kind of different sort of catalysts that are involved. Any questions on that there? So as I talked about before, our equilibrium is a condition where the rate of that forward reaction will equal the rate of the reverse reaction. And really where we see a lot of equilibrium processes is those transitions between phases as we go from solid to liquid or liquid back to solid. That's an equilibrium transition that occurs. It happens at the same temperature. For example, 0 degrees Celsius for water. When it reaches equilibrium, we got things kind of both phases happening in that situation. And also as you go from, say, liquid to gas or gas back to liquid, you also have that happening at equilibrium with each other at 100 degrees Celsius, for example, for water, which is a normal boiling point. by the way that happens at a surface of a liquid at any point, especially in a closed container, when they have this initial rate of evaporation that's going to occur, because those gas molecules really have nowhere to go, they're going to start condensating back down. And eventually, the rate of those guys jumping out, going through evaporation, will equal the rate at which they are coming back down in terms of condensation, and it will sort of equilibrate with each other. And that's also why you will sometimes see, I think, as we talked about maybe when we did vapor pressure, you'll sometimes see the low liquid level in a container like this come down just a little bit, because at the very beginning you have no sort of evaporation happening until it starts. And as it starts, it's going to lower the liquid level, but it will come back to equilibrium, and the overall liquid level will basically maintain. Any questions on that there? All right, I think that's a good place actually to lay it up.